So what is the length of the second shortest telomere? How do you calculate this? You need to be above the first one. So this, basically, you have your distribution of the lengths. You have the first one, which is here. So the second one, the probability distribution has to be, let's say, equals to an x. So let's call, what do you call f of z? This is for the second. So this is now the second shortest telomere. So f of the probability to be at x, you choose one among the two n, and then you have to choose the one that is going to be shorter. So shorter means that the length has to be distribution is f of x, and then the rest, that is the 2n minus 2, they have to be in this region. So this is exactly this to some power 1 minus f of x to the power 2n minus 2. 2n minus 2, is that correct? Yes, it is. All right, same methods, you calculate, you can now use, you take z, you take the mean, you take the integral from 0 to infinity of your x, fz of x, you integrate by parts. So you do the same type of methods. And what we found is that z divided by l, d divided by y, the mean, there was something universal, which was 1 plus 1 divided by alpha, where alpha was this 1 plus b. And so what we found is that the mean of z, when you plug all numbers, is 207. Now this was great. Why? Because you have now the minimum, what we call it y. This is the minimum one, the minimum size is here. Now you have your variance, plus minus 25. So how much is 25 plus this? This is about 200. And here lies our guy, z. Suggesting, again, this is just a suggestion, that probably the size of the minimum one, there is some kind of statistical separation which can be linked to the parameter of the problem. That this is, I would not say far away, but it is not, at least in the variant. This was important for us to check. That probably the cell feel or sense the shortest one when it reaches some kind of threshold. And this is the shortest that may be the key to trigger apoptosis, and not the couple of them, because obviously when this one reach a threshold, the other haven't reached anything, because obviously when you jump, you know, you do this -3 or this plus something. So if you are above this critical threshold, obviously the other might not be. So this was the reason we did this calculation.
David, are your values of L correct? Because L is up to 209, and 209 is obviously within the range of 207. I think your argument stands,
we are
just inside.
Okay. That's right.
Your argument stands, but it's just not quite right to say it's not in the range.
No. It's just in, you know, few base pair. Again, this is a suggestion. I'm not claiming anything. I'm saying from the statistics, there is no like a gap separation that you can have in eigenvalues where you have one very close to 0 and there's a gap. Here the gap is statistical. That is, you are not in the variance. This is the idea. You are not in the variance. There is no clear theory on this, so we had to make up something. That's all what we claimed. But what was interesting is to come out with numbers and to link this with to parameters, and to show that the statistical analysis could say something about the extreme statistic about the minimum, the shortest one. The next paper will be about when. That is, you ask the question. Now, if we go to mean field, in mean field you have a potential. Now, where is the threshold compared to the minimum of the potential? Where are you going to put it? You have the choice. I mean, we don't know where it is. So we looked at the situation where you have.
What potential again?
I'm sorry?
What potential? I missed that. Well, what
you were asking, what you had in mind, I suppose, is that.
Oh, you mean like in terms of fixed point?
That's right. When it comes to the analysis of this system, what you can do is you can derive, as you do in stochastic chemical reaction, you can calculate what is called the mean field. You look at the drift component for the stochastic equation, and you can see that the drift has the shape, it's the derivative of a potential well. This first moment. And so when you're here, basically, it's like you are going around also with fluctuations. Now you are looking at mean field. And so still you are interested in when are you going to reach, so for example, suppose you put your threshold here, when are you going to pass this threshold? So what we found, we haven't published all of this yet, so that you start from a long telomere, you're going to fall into this, obviously, because you're
That's
falling
very quickly, right?
very quickly, although compared to what? All right, no, this is a good question. This is a good question. So you are going to go in here with a certain time. What we find out is that the time it takes to go from here to here is of the same order as the time it takes to escape. Now this is very interesting, because then we calculated. Again, we haven't published this, but the idea of all of this, it says that telomerase is saving you about 30-40%, or extend the life of the cell of about 30-40%. It extends the life of a cell of 30-40%. The time that you would, now if you would have come to here, you're dead. Here you get stable, but the time to go from here to here is of the same order as to come to here, although this is much shorter. So you are basically maintaining in life close to the point where you are going to die.
So at the edge of stability.
That's right. Yeah, of stability to die. I mean, not die means senescence. Okay, I haven't shown this. This is much harder because this has to do with now calculating mean first passage time to the threshold for a jump process. And this is involved. It involved calculating Wiener-Hopf integrals, and this was not ready.